Yeah, drop, hey, huh.
Yo, what's up guys, this is 𝗪𝗏𝗟𝗟𝗟 and today we're gonna show a very old technique to bypass ASLR. So let's start analyzing our source code, and here we include some libraries, and then we have our main, and we see that we initialize a car buffer with 0x30 zeros, and then we have a printf message, inject me please and take this as a gift, and we see a %p and then the address of buffer. So we're gonna leak this, the address of the buffer, that we later on read into it. So here we can see buffer overflow, because it is 0x100 and the buffer is only 0x30, and the source code is pretty much this. We see that this time we don't have a function, for example a win. We see here nothing, no win function. So how can we actually exploit this challenge? We need to get cell, but we don't have a function that gives us a cell or reads a flag or do something. We only have this. So let's first of all see what the protections of the binary are. So we go inside GDB and we run check. Nice, and here we see we have parcel rel row, there is no canary, and as we explained in the previous examples, no canary means we can easily overflow a buffer, trigger a buffer overflow without the program exiting. And we also see here that we have no NX, GNU stack missing, and NX is unknown. That means that the NX bit is not set and we can actually execute code on the stack. Pi is not enabled, that means the addresses of the binary are not randomized. I mean the address is like main, and if we had another function and the gadgets and stuff. The libc addresses are always randomized because ASLR is enabled. And we also see that the stack is executable and the program has read-write execute segments. So let's first of all try and create this. This is a cyclic pattern, and we run the program, we insert it and see that the program crashes with a segmentation fault. And let's see where it stopped, cyclic-o, and we have this. We see that the offset is 56 bytes. So let's start writing our exploit also from pond import all, and we have our challenge which is fname, and we call it 𝗪𝗟𝗟𝗟𝗪. We forgot to compile it, so we're gonna use these arguments. No stack protector to remove the canary, no pi to disable functions randomization, and -z exec stack, meaning that we make the stack executable, and -w for warnings, and the output file is sc from 𝗪𝗟𝗟𝗟 with gcc, and we run the program and see this. Okay, we got this address, and we see that each time the program runs, this address is random. So as we saw here, let's first of all try and read the leak we have. So we're gonna do something like r.receive until, and we have gift, and let's read until here, and leaked buff is r.rec until, and we have this, and we don't want the bracket to be included, so we're just gonna do this, and let's try and print it. Print licked buff and have it here, licked buff, Python solver, and yeah, of course, our process f name. And we run it again and we see, okay, let's just do this here and this here to avoid warnings. And we see we have leaked this address. I don't like it this way, so we're also gonna do something like, we know that this is a hexadecimal value, but this is just bytes, so we're gonna use the int function in Python, and we know that this is base 16 because it's hexadecimal, and this way we're gonna convert it to an integer. Let's try and run it again, and we see, nice, we got a nice integer. This is easier to play around, but here we don't want like this. We want to print it in a format we can understand, so we're gonna go with this. And yeah, it's the same address, we just remove the bytes and stuff, and we actually converted it to int so we can use it later. So okay, this was the easy part to do. Leak and read the leaked address. Okay, so we actually managed to read the buffer that was given to us. But what can we do now? Okay, we know that we have a buffer overflow, we know the offset, we found the offset, right? Yeah, it's at 56 bytes, and we have the address of the buffer that we write into. But how can we exploit it? What can we do with that? As we said, the NX bid here is disabled. That means we can actually execute shellcode on the stack. What is a shellcode? Let's just move here, and we can see that at this site, shell-storm.org, we can find many shellcodes that do stuff. Here, for example, it gives us an execv syscall. Execv is it's very similar to system-𝗪𝗪𝗪𝗪, and here it's gonna execute execv 𝗪𝗪𝗪𝗪, and this is the assembly this shellcode produces, and these are the raw bytes like this, and the length is 27 bytes. It's given on the top. We can abuse the site to give us some nice shellcodes we can use, and as we said, shellcode is just bytes assembly that converts to syscalls like this execv, and we're gonna just take this, the whole bytes, and let's say we have our shellcode here like this. First of all, we're gonna use it as bytes. I don't like the double quotes, I'm gonna use this, and we have our shellcode right now, and we can put it our send line, and we can set our shellcode inside the buffer, and let's try and see actually what happens here. gdb.attach_r and r.interactive, and let me zoom out so we can see. Next instruction, don't worry, I will zoom out, zoom in again, and we see that, oh my god, let's see the bytes we have. It starts with one thing, I don't know why. Yeah, so it is 0x31, CO, C0, 48, and 31, C0, 48. So we see that we have actually written here, and this is where we wrote, so 20xgx here. And as we can see here, we started writing our payload 31, C0, 48, blah blah blah. It's the same until the 05, which is here. So we have filled the buffer until this place, and we see that we have many zeros here, another 0x10 zeros here, and then the RBP and the return address. As we saw from the previous examples, we know that these two addresses are. And our goal is, let's go to the stack again. So we're gonna fill the buffer, which is 56 bytes long. We start from 0, that's why here it's 55 and not 56. So we're gonna put our shellcode here, like this, and we're gonna have shellcode here, and then shellcode and shellcode, and probably shellcode until here. It's 27 bytes, so half of this is gonna be shellcode, and after that we still have zeros, and then we have the RBP and then the return address. So how can we proceed? We don't have another shellcode to input here, and we have a long way to go until we start overriding the return address. We're gonna proceed by, if you don't know, there is the so-called 𝗪𝗔𝗧𝗖𝗛. And what is a 𝗪𝗔𝗧𝗖𝗛? If you go to Wikipedia, you can say that 𝗪𝗔𝗧𝗖𝗛 or 𝗪𝗔𝗧 or 𝗪RAMP is a sequence of no operation instructions meant to slide the CPU's instruction execution flow to its final desired destination. So a 𝗪𝗔𝗧𝗖𝗛 is actually an instruction that does nothing, just lets you continue the program. If you hit on a knob, it just ignores it and goes to the next instruction. So if we proceed, and here we start adding some knobs, which is 90, 90, 90, 90, 90, and then another 90s and another 90s, and RBP of course another 90s. Then the program is gonna reach the return address, which we want to overwrite. And overwrite it with what exactly? Okay, we have managed to reach destination, and now what? There is no win function, there is no something we can call actually to get cell or to get the flag. But is it? If you remember, the shellcode we have entered here is actually giving us cell. It runs the command exec_v_bin_sh. Our goal is to somehow go here. If the program goes here as the next instruction, it will start executing whatever it finds in this buffer, which is exec_v. And if we remember correctly, here inject me please and take this gift. It gives us the address of the buffer that we write. And for this run, I'm gonna take this as an example, and imagine that this address here is this. We actually get this address, we know it, and here in our previous examples we did something like wet, and we overrode the return address with the wet function and executed whatever wet function had. In our case here, why not trying to do something like this? Override the return address with the start of the buffer, which has our payload. We have entered our shellcode here, our payload, and then we tell the program, okay, forget what you had as a return address and go right here. So the program will go right here, and because the NX bit is not set, the program will start executing whatever it has in this buffer. And let's try and make the solver from here. We have leaked the address, and we have the exec_syscall like this, and then what else we're missing? We are missing the 𝗪𝗪𝗟𝗟𝗪, right? And we can actually use this. We need to fill the rest with stuff like this, this is 0. We're gonna do stuff like this, the 𝗪𝗪𝗟𝗟𝗪, and instead of doing it manually, we can use the 𝗪𝗔𝗧𝗖𝗛 function and tell them that we want to add 𝗪𝗪𝗟𝗪𝗪, and we want, what was the offset? 56. We want the 𝗪𝗟code to pad it with 𝗪𝗪𝗟𝗪𝗪 until it reaches 56, which was the offset that we override the return address, and after that we need the actual buffer that we have leaked, where we store our payload. And the payload should look like this. We have, first of all, we leak the address of the buffer that is given to us. Then we find a nice payload, a nice 𝗪𝗟code to have, and as we said, we got it from cell-storm.org, and then we adjust, because this is 27 bytes, we want to make it until 56 in order to override the return address, so we just pad it with 𝗪𝗪𝗟𝗪𝗪 until it reaches 56, and after that we are like this. We have 27 bytes of 𝗪𝗟code, 𝗪𝗪𝗟𝗪𝗪, and then finally at 56 we start overwriting the return address. This is a mistake here, like this, and we tell him, okay, instead of returning wherever you want it, go here, so go to our buffer and start executing the 𝗪𝗟code. And let's see if this actually works. If it works, we should get cell and Python solver, and as we see, we have an interactive cell ID, I'm wet hands, who am I? We see that it works. We actually got cell, and this was the technique called ret2shellcode. Let's see if this works with no pi, with pi actually, and I'm pretty sure it should work. Yeah, it worked again, because we don't rely on something that is pi related. We get the leak and we just perform an overflow. But will the technique work if canary was on? So if we go like this, and we see that we didn't get cell this time, ID, nothing, program exits, and we got the stack smashing detected, because the canary is on. We altered it after overwriting, before overwriting the return address, and that's why the program stopped. And this, guys, is one of the oldest techniques. It's called ret2shellcode, and we can do it to bypass ASLR, when we have a leak on the stack, or when the program executes directly the code we give it, and the only thing we need to do it is have the NX bit disabled and or have canary disabled. In some cases you want it, in others not. If you guys have any questions, leave a comment, like the video and subscribe to the channel. Thank you for watching and see you on the next one. Bye.